Now we can see it. Thank you.
Do you see it now? Okay, great. Also, if I go to the next slide.
Yes, you're perfectly visible now.
Okay, thank you. Okay, so very brief overview. I'll start with a bit of motivation, then give a brief introduction to weighted projective spaces and to height functions on these, and then mostly talk about applications to modular curves, and end with a bit of work in progress. And I'd like to mention that parts of this talk I joint work with Philip Neumann and with my former master student, Irati Monterola. Okay, so yeah, as I already mentioned, this is about genus zero curves, which might sound a bit boring at first. But well, this is the setting in which you usually expect infinitely many rational points. And then we want to count with respect to a suitable height function. So we can quantify how common or how rare it is for elliptic curves over number fields to admit a given level structure. And it turns out to be much more subtle than you might expect. It doesn't just depend on the fact that you're on the genus zero curve. Also, the fine structure of the modular curve plays an important role. It's really about the structure of the moduli stack, not the coarse moduli space, which will be P1. And also, you can view this as an application, as a proof of certain instances of the so-called stacky Batyrov-Manin conjecture about counting rational points on varieties for interesting stacks that occur in nature. And just in case you're worried about the language of stacks, I'm not assuming any knowledge of stacks in this talk at all. So they will appear at some point, but you can just think about more concrete sets which will appear. By the way, don't hesitate to ask any questions. Okay, so to start off, let's start with the most basic setting where you have an elliptic curve over Q. And then we know we can choose a minimal short Weierstrass model. So you choose the coefficients to be integers. A and B have to be satisfy this inequality that the discriminant of the curve has to be non-zero. And minimal means that there is no prime P whose fourth power divides A and whose sixth power divides B. So let's call AB a primitive pair of integers. And then we define the height of the elliptic curve E as the maximum of A cubed and B squared in absolute value. And you've probably seen other measures of complexity of elliptic curves, discriminants, conductors, or Faltings heights. So I'm choosing this one because it's most natural in the counting setting that I'm going to talk about. Of course, it's also very interesting to count by these other sizes, like counting by discriminant or by conductor, but I won't talk about that. So the very first question you would like to ask is, how many elliptic curves of bounded height are there to start with? So by this parameterization using integers A and B, this just comes down to counting integral points in a box. So the size bound, the height bound on E means that A has to be in between minus t to the 1/3 and plus t to the 1/3, and B has to be between minus t to the 1/2 and t to the plus 1/2. So then the number of integral points is just essentially the area of the box, except we have to take out the non-primitive points, and then you can look at the probability that both A is divisible by p to the 4th and B is divisible by p to the 6th. And it turns out that to get only the primitive points, you have to take a fraction 1 over zeta of 10, where zeta is the Riemann zeta function. So then it's not hard to deduce the theorem that the number of primitive points in this box, or equivalently the number of elliptic curves over Q with height bounded by t, behaves asymptotically like 4 over zeta 10 times t to the 5 over 6. So this tilde sign means that the quotient of the left-hand side by the right-hand side tends to 1 as t goes to infinity. Okay, so this is just a kind of warm-up question. Now we're going to add conditions. So motivation for this work was originally to generalize a result by Rob Heron and Andrew Snowden from some years ago, who counted the number of elliptic curves with a given torsion subgroup. So by Mazur's theorem, the possible torsion subgroups for elliptic curves over Q are cyclic of order n, where n is between 1 and 10 or is equal to 12, or C2 times Cn, where n can be 2, 4, 6, or 8. And what they proved is that for any of these groups, there exists a positive rational number d gamma, such that, and now there's a slightly different symbol, not this tilde, but this other, say, growth rate symbol. The number of elliptic curves with torsion group gamma and height bounded by t behaves like t to the 1 over d of gamma, but only in the sense that the quotient of the left-hand side by the right-hand side is bounded by some constant from above and below. So we don't yet have a limit statement. Now, I'll come back to that later. They did prove a more precise statement in the first few cases where gamma is trivial. That was actually the result we just saw on the previous slide. When gamma is C2 or C3, in each of those cases, it turns out that there is the more precise statement that the left-hand side is asymptotically equivalent to an explicit constant, which will again involve some zeta functions and rational numbers, times t to the 1 over d of gamma. And they also gave a way to compute this d of gamma for each of the groups gamma. So very briefly, their method of proof was to parameterize the family of elliptic curves with this torsion subgroup by two polynomials f and g. And if you plug in rational values of t in these polynomials, you get a rational elliptic curve, an elliptic curve over Q. And then you have to estimate how many values of t give rise to elliptic curves of height bounded by t. So there you have to be careful because there might be some cancellation for some values of t that gives you a smaller height than you would initially expect. Okay. So our initial motivation was to take this result and try to generalize it to number fields. And at first, so with Philip Neumann, we started with determining the growth rate, so generalize the theorem by Heron and Snowden for elliptic curves over number fields. But the first problem we ran into is that it was not clear what notion of height to use. So we had to try several possibilities before settling on one notion of height, which already turned out to exist in the literature, but was not very well known yet. And in hindsight, this was one of the first examples of a height on a stack. And in recent years, there has been a lot of development in defining these heights and proving properties that allow us to count points of bounded height. So next, I will want to focus on weighted projective spaces. So geometrically, a weighted projective space is like an ordinary projective space. You take an affine space, take out the origin, and quotient out by an action of the multiplicative group. We replace the standard action of the multiplicative group, which is just scalar multiplication, with a weighted version, where we choose a tuple of n+1 positive integers. And we let a scalar lambda act on the ith coordinate by multiplication by lambda to the power wi. Okay, this is the abstract definition. In practice, we'll mostly be looking at the k points for a field k. And then it is really what you expect. It is you take k to the n+1 minus 0, and you quotient out by the action of k star given by exactly the same formula. So now it is important that this is not the set of k points of a variety. So you can also define weighted projective spaces as varieties, but we are not doing this. And one of the important differences is that if you take a field extension of k, say L, then the map from the K points to the L points is not necessarily injective. It can happen that 2 points become equal over L, whereas they were not equal over K. This will also be a subtlety when defining height functions. So the height function will depend on a finite and an infinite part. So now we restrict to the case where K is a number field and a W is a tuple of weights as above. And then starting with the finite part of the height, this is defined in terms of an ideal attached to a point X. So remember that in the setting of elliptic curves, we could make sure that our representative AB of the coordinates was primitive. Since arbitrary number fields don't necessarily have class number 1, and also there are units, it's no longer possible to choose a unique minimal representative or even any minimal representative. So we have to measure the defect for each prime, how far our point is away from being primitive. This is measured by the scaling ideal, which is the unique smallest fractional ideal A of K, such that X is contained in A to the W0 times ... times A to the Wn. There's also a different definition where it's more clear that this only depends on the behavior of X at each finite place separately. But I don't want to write that down here. So that's what's going to come in for the finite part. Then the infinite part is given by a product over all the infinite places with an expression you're familiar with if you've seen heights on projective spaces before. It's for each place V, you take the maximum of the v-adic absolute values of the xi. The difference is that you have to take each of these absolute values to the power 1 over wi. So with these finite and infinite contributions, we now come to the definition of a height function on this weighted projective space. This was originally given by Deng in 1998 in an unpublished preprint. He defined the height, or the size as he called it, as the function which sends x to this Archimedean height divided by the norm of the scaling ideal. So to give you one concrete example, which is connected to the setting of elliptic curves, if I take x, so the a and b that we had before, to be 2 to the 5 times 3 squared and 2 to the 7 times 3 to the minus 4, then, for example, you see that if you think about scaling back to a primitive point, that you can divide a by 2 to the 4 and b by 2 to the 6th. So there will be a factor of 2 in the scaling ideal. And to make it integral, you also have to multiply by a factor of 3, which explains that there's a denominator of 3 in the scaling ideal. So then the infinite height will be the maximum of a to the power 1/4 and b to the power 1/6. That turns out to be a to the 1/4. And combining this, you see that the height of this number is 2 to the 1/4 times 3 to the 3/2. Okay, and the reason Deng introduced this height function is that it allowed him to count rational points on these weighted projective spaces. He proved that the number of points of height bounded by t behaves asymptotically like a constant CWK times t to the absolute value of w. This is just the sum of all the wi's. And the CWK is a very explicit constant which depends on algebraic number theory invariance of K, like discriminant, regulator, and class number, and also on the choice of W. So a couple of remarks. So Deng actually was not thinking about stacks when he wrote his paper. He restricted to a case where if you have your tuple of weights and you take out any of them, the remaining ones are still co-prime. This guarantees that the quotient is in fact a variety. But this is barely used at all in the proof. And it turns out you can just remove this restriction and then it is really a point counting results on an algebraic stack. And this generalizes a classical result by Chenyol, who counted points over number fields on ordinary projective spaces. Yeah, so I said before that this is nowadays viewed as a special case of more general height functions. The ones I want to mention in particular are the heights on stacks introduced by Ellenberg, Satriano, and Zurich-Brown, a very general setting in which to define heights, and also by Ratko Darda, who introduced the whole family of heights on weighted projective spaces and proved results similar to Deng's for these more general heights. I hope to come back to that at the end. Okay, so now we can use this weighted height to also define heights of elliptic curves over general number fields. And it's convenient to slightly modify the previous definition where we just took the maximum of a cubed and b squared. In the concrete calculations, it turns out to be easy to take the standard C4 and C6 invariant of E, which are just certain multiples of the A and B, which I showed before. So if you take an elliptic curve over a number field K, then it has a C4 and a C6 invariant, which are defined up to scaling by the 4th power and the 6th power of a scalar in the base field, respectively. And this means exactly that the pair C4 and C6 corresponds to a point on the weighted projective space P46 over K. And we take the height of this point to be our definition of the height of the elliptic curve E. And it's useful to note that of the types of the other types of height that I mentioned before, so the discriminant height or the conductor or the Faltings height, this one is closest to the Faltings height. In fact, if you take the logarithm of this height, you can compare it to the Faltings height. So that for those of you who know about Faltings height, this is the unstable Faltings height. However, the difference is still unbounded. So you could try to use the comparison to also count elliptic curves with bounded Faltings height, but so far we haven't worked this out. And so let me also remark that already this result of Deng that I showed before now immediately allows you to count elliptic curves in the sense of the beginning, so elliptic curves of bounded height over any number field. But now we want to do this for elliptic curves with additional level structure. And it turns out that the setting in which we're able to do this is the setting in which the corresponding modular curve itself is also a weighted projective space, like P46. So the setup is going to be as follows. We take a modular curve xg, defined by a subgroup G of GL2 Z mod nz for some positive integer n. And we assume that if you take the compactified moduli stack in the sense of the Ligne and Rappaport, this is isomorphic to a weighted projective space of dimension 1, which I will call a weighted projective line. So it will be of the form P, W0, W1 for some positive integers, W0 and W1. So since we always have the map xg goes to x1, which just forgets the level structure, and we have our fixed isomorphism of x of 1 with P46 given by the C4 and C6 invariants, we can make a commutative square where we translate this forgetful map pi g into a morphism of weighted projective lines from PW to P46. And it turns out that the morphisms between these weighted projective lines can be classified in a very concrete way. And it just means that there exist homogeneous polynomials with coefficients in Q. So I'm making one simplifying assumption, which is that the group consisting of all the determinants of elements in G is all of Z mod n Z star. That tells us that everything is going to be defined over Q. And there will then be homogeneous polynomials F0 and F1 over Q, whose degrees are 4e and 6e for a certain integer e. And the map is then expressing C4 and C6 as these polynomials in A and B. And homogeneous here means that I give A weight W1, degree W0, and B degree W1, and then F0 and F1 should be homogeneous of these degrees. So one concrete example is the curve x1 of 3, classifying elliptic curves with the 3 torsion points. And then the diagram looks as follows. The one convenient choice of coordinates is the A1 and A3 coefficients of the elliptic curves, of the elliptic curve, where we multiply the A3 coefficient by 6. So we call these parameters A and B. And then you can express the C4 and C6 invariants of the elliptic curve as these polynomials. C4 equals a to the 4th minus 4ab, and C6 equals minus a to the 6th plus 6a cubed b minus 6b squared. And if you compare the degrees, then you see that this integer e is just equal to 1 in this case. So yeah, you can write these things down for any modular curve which fulfills this condition that it is a weighted projective line. You get polynomials in each case. And for the first application, it's actually not even necessary to know what exactly these polynomials are. So the theorem I want to explain now is what came out of the project with Philip Neumann, where we did manage indeed to generalize the theorem of Heron and Snowden to elliptic curves over number fields. So we're going to look at pairs E, alpha, where E is an elliptic curve over our fixed number field K, and alpha is a G-level structure. So think of cyclic subgroup of given order or torsion point of given order. And we count elliptic curves such that the height of E, in the sense we defined before, is bounded by T, and we call NGK of T the number of these isomorphism classes. So something I did not mention yet is that these heights on weighted projective spaces, they do have this Northcott property in the sense that the number of points with bounded height is finite. So this number actually makes sense. And our theorem then is that under one additional assumption on our setting, namely either the two weights have to be 1, 1, so that the weights for which xg is isomorphic to pw, or this number E has to equal 1. Then, like in the theorem of Heron-Snowden, for any number field K, this number of points is has the growth rate T to the 1 over D of G. And now we can also explain where this number D of G comes from. So in the paper of Heron and Snowden, this is a bit tricky. There's not an immediately obvious expression for this. You have to look at the degrees, but also common factors of f and g play a role. In our setting, we can just compute D of G as 12 times E over the sum of W0 and W1. And it turns out that all of the modular curves that Heron and Snowden looked at, namely all the modular curves classifying elliptic curves with one of the possible torsion subgroups that appear over Q, they all satisfy this property. In addition, a few more, like elliptic curves with a cyclic subgroup of order 4, not necessarily consisting of rational points, but the subgroup itself should be rational. So x0 of 4 is another example. satisfying our conditions, and a few more complicated ones as well. Any questions so far? Okay, then let me continue with the next question. So now that we have this growth rate, we'd like to know if, similar to the result that Heron and Snowden also proved for torsion subgroups C1, C2, and C3, if this can also be generalized, can be refined to an asymptotic formula. So you would really like to have a constant CGK, depending on the level structure G and the base field K, such that NGK of T, so this counting function defined here, of the dispersed E alpha, really has the property that if you divide it by CGK times T to the 1 over D of G, then the quotient will tend to 1. So the reason we were not able to prove this initially was that we used Deng's result on this point counting as a black box. So we're using, in the setting of this diagram, where we're using both the height function on P46, which gives us the height of E, and we're comparing it to the height function on PW. And this is a bit too coarse to get the most precise counting result. And this is also a good place to mention related work by Boggess and Sankar, who around the same time as we were working on our project, were working on a different direction of a different way of generalizing Heron and Snowden's work. Namely, they were looking at elliptic curves over Q with a cyclic anisogeny. So they looked at more general modular curves, but the base field Q. And surprisingly, there's only a fairly small overlap between their results and ours, because not many modular curves x naught of n have the property that they're isomorphic to a weighted projective line. But in a similar way to our setting, they use methods which also don't immediately allow them to give an asymptotic formula. They just get the growth rate. So the question is, what should you do to prove these more refined results? So let me first give a list of cases in which this had already been done. At the very beginning, I already gave you the formula for x of 1, so just the number of elliptic curves over Q of bounded height. In the literature, this was first in a paper by Broomer from 1992. Then Grant in 2000 did the same thing for elliptic curves with the 2 torsion point, or equivalently a 2 isogeny. Part of the theorem of Heron and Snowden is that you get an asymptotic formula for x1 of 3, elliptic curves with a 3 torsion point. And then in a paper by Pizzo, Pomerantz, and Voigt, they treated the case of a 3 isogeny, and Pomerantz and Schaefer a year later, the case of a 4 isogeny. So all of these are fairly specific to the case Q. Every time it's about counting points in certain regions, satisfying a number of congruence conditions. And then, you have to use increasingly sophisticated techniques to get accurate estimates for these number of integral points in these regions. So what we had to do in the end to get these asymptotic formulae is to generalize the result of Deng to more general height functions. Namely, instead of taking the standard weighted height on PW, we take the pullback of the height function from P46, again under this map pi g. So essentially, we have to reprove the results of Deng for a more general family of height functions. And so this results in a theorem that was proved simultaneously, first of all, by myself and a master student, Irati Monterola, So the master's thesis project was done in 2021, and we finished preprint based on this 2023. In the meantime, Tristan Phillips in his PhD thesis had been working on the same problem. And in fact, there was some nice interaction where we both found some mistakes in each other's work. And in the end, well, we got a common result, even though the approaches are still partially different. And what comes out is that under the same assumptions as before, so in the theorem with Philip Neyman that I showed before, we can refine the result to an asymptotic formula. Ngk of t is asymptotic to Cgk times t to 1 over this dg. And Cgk now depends on a few more things. So in the starting result of Deng, this was for the weighted projective space. You just had these algebraic number theory invariants of k. Now there are also invariants coming from this morphism phi, or equivalently of these polynomials f0 and f1. And these are things like the area of a certain region where the absolute values of these polynomials are bounded for each of the Archimedean places. And also there are congruence conditions that measure how the scaling ideal changes, so that the finite part of this weighted projective height. So it could be that the scaling ideal of the point that you start with on PW is different. For example, could be larger once you map it to P46 by this map phi. So yeah, apart from just generalizing the strategy that General used to count points on Pn of k and then for Pw of k, we had to make a few modifications. So I mentioned these congruence conditions, and to do the point counting part of integral points in a region, we had to use a fairly recent result by Barrero and Whitmer, who proved a quite general lattice point counting theorem for so-called definable sets in an O-minimal structure. So again, I don't want to go into this. It's actually less intimidating than it might sound at first. It's really about nice regions, like regions bounded by polynomial inequalities, and maybe logarithmic expressions in logarithms or exponentials. It turns out that for any bounded region of this kind, you can have a fairly general lattice point counting result. Okay, so then I would like to talk about possible generalizations, because as I said before, this is still under the assumption that we are in the setting of a weighted projective space. So Xg is assumed to be a weighted projective space. Also, we have this additional condition W equals 1, 1 or equals 1, which really seems to be fundamental. But at least, so that condition is satisfied in all the cases that we can find. All the modular curves that are isomorphic to some PW by some coincidence, or maybe there's a reason which we don't know. They do all satisfy this condition that W equals 1, 1 or equals 1. But yeah, the most important obstacle is that many modular curves are not weighted projective lines, even if the underlying coarse moduli space has genus 0. So by looking at one of the first examples of this, X0 of 3, which I'll come back to in a minute, it appears that the tools that have been used so far don't seem to be easy to generalize. So fortunately, there is also the recent work about more general heights on stacks. And the type I want to talk about a bit now is more general heights on weighted projective spaces. And then try to also generalize the weighted projective space to something more general. So this is done in the recent PhD thesis of Rodko Darda, who was a student of Antoine Chamberloir. And he extended previous work of Batyrov and Chinkel, and also of Chamberloir and Chinkel, and people in this area in the whole point counting business on sufficiently nice varieties. So there's the Batyrov-Manin conjecture, which predicts for Fano varieties, so sufficiently nice varieties, which are a bit like projective spaces, say, how the number of rational points should grow as the height increases in terms of geometric invariance of the space. So there are now conjectures which are fairly refined. We also say you have to take out some sub-varieties maybe which have more points than expected. And then, there are conjectural asymptotic formulae for the number of rational points up to bounded height, involving again some explicit constant which you can put in front, and a power of t and maybe log t. And one of the tools that has been used with a lot of success is harmonic analysis on adelic groups. So an important feature of this, of the projective space, for example, is that it has a large open subset, which is a torus. So you take some n-dimensional torus, so nth power of gn, and the k points in this form a lattice inside the points of the Adel ring. So AK is the ring of Adels of k. And if you want to count k points, then the method that they use is to define, first of all, a zeta function based on the rational points. So here, for the moment, you can first think about the standard action of k star on k to the n minus 0. If you look at the sum, then you get a projective space. Then, so Darda showed what happens if you replace this action by a weighted action. So you take the heights. So the height can be any height in a certain family, which he defines. You take these heights of the point x to the power minus s. And then for the real part of s large enough, you get a convergent series, which is called the height zeta function. And then a way to analyze this sum is to apply the Poisson summation formula on it inside this adelic version of the torus. And then you can show that there is an analytic continuation for this zeta function, and it has a pole at s equals 1, whose behavior dictates how the number of rational points grows via suitable Tauberian theorem. So this is, in a sense, quite a bit more sophisticated than, just the more naive methods of counting lattice points in a region. But it really seems to be applicable in a wider setting. So I was talking to Chamberloir some time ago and told him about this x0 of 3 that I was thinking about. And he suggested using this approach to try to count the points on that. So that's the last thing that I would like to discuss. So even though x0 of 3 is one of the smallest modular curves, from the point counting perspective, it's still fairly elusive. And the way I like to view this is that it is not a weighted projective line, but still, tantalizingly close to one. It's, for example, isomorphic to a weighted projective point. So P2 is, this is one of the nice features of stacks. Even if it's 0-dimensional, it's still arithmetically interesting. So there's an interesting weighted projective point, P2. which is also the classifying space for mu2, for those of you who know about that, times a weighted predicate line P13. And this P13 can be identified with X1 of 3. And well, it is accessible enough in the sense that over Q, there is already this asymptotic formula that I mentioned before in this list. Pitso, Pomerance, and Voigt proved a few years ago that if you count Q points on X0 of 3, then actually you have a very specific asymptotic behavior where they don't just give one, but even 3 terms. And the first one is C0 to the power T1/2 for, again, some explicit C0 involving a zeta value and a rational number. But in contrast to the other cases, this comes only from twists of a single elliptic curve. So this is something that never happens in the case where you have a weighted predictive line. So this is one of the distinguishing geometric features. And that is very similar to this phenomenon in the Batyrov-Manin conjecture, where you have to leave out certain subvarieties because they contain too many points. So that is just the twists of a single elliptic curve. And if you remove that, then you get 2 terms, t to the 1/3 log t with some coefficient, and t to the 1/3 with some other coefficient, which count the remaining elliptic curves. Yeah, but again, yeah, their method seems to be quite specific to the case Q. You have to look at a certain 2-dimensional region, and it's hard to imagine what this region looks like if you replace by Q by a number field. So currently, I'm trying to apply these harmonic analysis techniques of the people mentioned here, Batyrov, Chinkel, Chamberlain, Chinkel, and Darda, to this case. So even though this is not a weighted predictive space, it still has a similar structure. So now instead of an affine space, so in the previous applications, this was just an affine plane, quotiented out by GM. We now have a 3-dimensional affine space with the origin removed, quotiented by a 2-dimensional torus. So this seems to be a slightly more convenient description of the curve than the P2 times P13, which I mentioned before. So what you do is you let GM squared act on this space by, so lambda mu acts like you multiply the first coordinate by lambda squared, the second coordinate by mu, and the third one by lambda squared times mu cubed. And then you look at the map sending this space to the C4, C6 line, so to X1. And that defines a height function on this torus quotient, which behaves very much like one of these quasi-toric heights that Darda studies. And even though, some of the technical details still need to be generalized, it looks like this is going to work. So the work in progress, which hopefully I'll be able to report on in the future, is to generalize Darda's techniques to quotients of this kind, and thereby hopefully generalize this counting result of Pitso, Pomerance, and Voigt to the case of number fields. And then we can try to look to other modular curves, which you can also write them as a similar quotient. So hopefully this will be the topic of a future talk. So I'd like to stop here. Thank you for your attention.
Thank you very much, Peter, for that wonderful talk. Any questions?
Yes, thank you for the talk. I have a question about X0 of 3. Can you go to the previous slide?
Yes.
About this leading term, I have no intuition of this. What would you expect for a higher degree number field? Would this leading term still come from the same elliptic curve, or would it sort of disappear?
Yeah. For general number fields, I expect that this is going to happen again for the same elliptic curve. So j equals 0 with the particular order 3 subgroup. You can see this a bit by looking at the formula for this weighted action, which is also on this slide. So the point or the points corresponding to this curve are the ones where the second coordinate vanishes, so v is 0. And then you have more freedom in choosing this mu somehow. So if you have a point where v is non-zero, then multiplying it by any mu would probably increase this height a bit. But if you if v is, there's a typo here. The last coordinate should be w, the lambda squared mu cubed w. So if you now restrict to the case where w is 0, or v is 0, then it turns out that you can exploit cancellation between the lambda squared and the mu cubed acting on w, which will give rise to many points of small height. And this will also happen over number fields.
Okay, so it means in the context of Batyref-Manin, it really comes from a geometric region where points accumulate, right?
Yeah, it really comes from a geometric phenomenon on this quotient. Yeah.
Right, thanks.
Yeah, except in the sense it's now a zero-dimensional subvariety, which has a lot of points, so which is intuitively a bit odd to think about, but that is what happens.
There's one more question.
Hi, Peter. Thanks for the talk. I actually have several questions, but I'll try to keep it short. So one is this comparison between your height and the faulting height. So you said they can be compared, but the difference is still unbounded. What did you mean exactly? Is the ratio bounded or?
Yeah, so when I said the difference is bounded, I was thinking about the logarithms of the height, so the logarithmic faulting height and this one. I don't know about the ratio of these logarithmic heights, but what I can say is that the reason for this difference is purely something that happens at the infinite places. So it just turns out that the infinite contribution from of the faulting height looks a bit different than the infinite contribution for this height, but it's a very in terms of some suitable coordinate, it's only logarithmic in a vague sense. So for most curves you expect them to be quite close together, except when the J invariant goes to infinity, then they slowly diverge.
Okay, and another question is maybe a bit vague, but so I think there are general conjectures, these generalizations of Batyref-Manin to stacks. So even if you can't prove anything, but do you have at least conjectural asymptotics over number fields?
Not yet, but there is a recent paper of Darda and Yasuda where they give a stacky version of the Batyref-Manin conjecture, and I think also Ellenberg, Satriano, and Zurich Brown have versions of that. I haven't yet looked into whether the case of x0 of 3 would follow directly from one of their conjectures. But if it turns out that it's hard to prove a theorem, then at least it's still worth looking what the conjecture would be. And of course, if there is a theorem, then I would like to compare it to the conjecture.
Yeah. Thank you.
Yeah, so I just had a question. So are there any generalizations known for this result of Heron and Snowden over function fields, over the rational function field, finite field?
That's also a good question. I don't know if this has been done. but I guess it should be possible. Yeah, you can define heights over global function fields. Yeah, I don't see an obstacle that would prevent this. But, I haven't looked into it, to be honest.
Thank you, Peter, for your wonderful talk. So here the question I have is, like x naught of 3, you said is isomorph to P of 2 cross P of 1 comma 3. So how do you show this?
Sorry, can you repeat?
No, the first line, the first two lines, that x naught of 3 is isomorphic to P of 2 into P of 1 comma 3. So how does one prove this?
So essentially, this is because an elliptic curve with a 3 isogeny after twisting becomes an elliptic curve with a 3 torsion point. So you have to be a bit careful, because it's not the case that if you take any two of these modular problems like x naught of 3 and x1 of 3, where the only difference is kind of in index 2 subgroup in the groups defining the modular curves, it's not automatically the case that one of the modular curves will be P2 times the other. But in this case, it happens that is the case. So you can really think of the P13 as being x1 of 3 and P2 as classifying the twists.
And in general, is there any kind of a structure theorem kind of thing saying that it looks like this and then we have to eliminate and figure out the values?
No, not really, but there is a connection to rings of modular functions, or rings of modular forms. So the way actually we found our list, so Philip Neumann and I found our list of modular curves that are weighted projective lines, is by using the fact that that happens if the ring of modular forms of varying weight for the corresponding congruence subgroup is generated by two homogeneous elements. Mm-hmm. So yeah, the way I would approach this is by computing spaces of modular forms, and then from the structure of this ring of modular functions, modular forms, deduce a model like this. But yeah, I don't know if it's easy to write down a general formula.
Okay.
When the group varies.
Previous slide.
Sorry?
You go to the previous slide.
The previous slide?
Yeah, the last two lines, the behavior at pole s equal to 1 actually translated into asymptotics. So just could you elaborate a little more how we can get the information?
Sorry, could you repeat your last sentence?
Last two lines, just can you elaborate a bit?
About what's the question about the last two lines?
Can you explain a bit more about the last two lines, that the behavior?
Can I explain a bit more? To be honest, I'm just using this as a black box. But what it tells you is that, so maybe I should show this formula by Pitzel, Pomerantz, and Voigt. They were not using this method, but you see that if you remove this leading term, then you get 2 powers, so 2 terms with a t to the 1/3 and a log factor. And this is the kind of thing that comes out of this Tauberian theorem. If you have a higher order pole at s equals 1, then you will get a corresponding sequence of terms with different powers of the logarithm. So it's going to be a certain power of t times a polynomial in log t, whose degree is the order of the pole -1, if I'm not mistaken.
Yeah, thank you, Peter.
Okay, so if there are no further questions, let's thank Peter again for his great talk.